Hello class, I am working from your Algebra 2 book, Chapter 3 on general graphing and maximizing examples. If you're asked to solve graphically and are given a couple of expressions such as x plus y equals 5 and negative 2x plus y is greater than 2. Remember to work from your y equals mx plus b formula, where b is the y-intercept. So thinking about that, let's solve the first one and put it in that form. And we'll go ahead and look at the second one. Put it in that form as well. Y is greater than a positive 2x plus 2. That will help us get started. You're asked to solve graphically. That means you're making a visual on the graph from the expression. So let's do that for our first one. We know we have 5 as a y-intercept. That's at 0, 5. And then we have a negative slope. So in invisible math, that'd be a 1, but the rise over run would be a negative 1 over 1 for the actual slope in the expression. So be sure your graph visually has a negative steepness to the line for slope. So working negative for rise over run of 1 over 1, we're going to be plotting our points here. And this graph emerges. For the second equation, we have a greater than symbol. We have a positive slope of 2 over 1 and a y-intercept at 0, 2. So we're going to rise to run 1 and start plotting our points. Rise 2, run 1, and our graph emerges. But when we graph an inequality of greater than, we don't just put a solid line because there's no equals in that inequality. So you actually annotate this with a dashed line, like this, to represent the greater than symbol without an equals. We do have an intersection point of the two lines, but we were just asked to solve graphically. So we plotted both expressions on the Cartesian plane and showed where they would graph, and we do get an intersecting point. Okay, moving on. If you're given an expression such as z equals 5x plus 10y, and you're asked to maximize based on an illustration you're given on the plane, for instance, you might have something like this in your illustration. It's not perfect, but we get the idea. All right. And this is the shaded area. All you have to work with for x and y is what you actually see on the illustration. So pull those points that are already plotted at the intersection points for deciding where your maximization of that expression will be. How do we do that? Well, we look at the 4 points that emerge in the intersections. We plug those x and y plotted point values into the expression we're given to solve for the biggest solution that we can find. Let's do that. So we're going to say, okay, we have an expression for z. I'm going to look for my plotted point at 0, 0 and plug it in. So we'll do that. We plug in 0 for x at the origin, 0 for y at the origin, and our answer is 0 for our first test. Let's try the plotted point 0, 5. We'll plug in 0 for x and 5 for y here, and we get 50. That's a pretty big number. Okay, so we'll try again. We have another plotted point to test, and we see that it's at 3, 3. We don't have to test for the intersection point here. We can just see it on the graph. It's probably pretty close for this purpose. So 3 for x in the original expression plus 10 for times 3 for y. And we get 15 plus 30 is 45. We have a fourth plotted point at 3, 0. Let's try that one. So we're going to have 5 times 3 for x plus 10 times 0 for y. That is 15. So out of our test points, based on what we're given on the graph, when 0 for x and 5 for y are plotted and tested in our expression, that's our maximum value. So we'd say that. We'd say, well, z of 0, 5 equals 50 for our answer, showing that that's answering the question of our maximized value for that expression. I hope this helps, and I will see you soon.